All right, so I think we're gonna get started here. Um, Linda is our gonger, and you will hear the gong. Yeah, and Linda is very excited to gong. So if you go over, you better be ready because Linda is gonna gong you.
Let's share the rules.
Oh, rules, yeah. Okay, so we have
We're excited about all of you. We're excited about all of you being here today.
I'm getting there. Thank you, Jessica, for your help. No, I'm really excited to be here. I think this is an awesome opportunity to hear quickly of kind of like things that are happening in the college. And we did this last semester with faculty, and we plan to do it again in the spring. And I hope that we carry this sort of tradition every fall, or maybe even more often with our grad students, or even our affiliate programs, whether it be like chemistry, physics, mechanical, electrical, whatever. Because I think it's really important for us in this building of the community to kind of be able to talk about why we're here, right? And so we have these 9 presenters that are going to present briefly these lightning talks in this I was warned how to say this. These are lightning talks, but they're 3-minute thesis style talks, because 3-minute thesis has a trademark. But we're doing lightning talks that are 3 minutes, and they're the style of 3-minute thesis. Anyways, it's a cool way where we can go through a lot of things quickly. And I know that the 9 presenters have put a bunch of time into the 3 minutes, and I think for those of you that didn't prepare for this, preparing for a 3-minute presentation can sometimes take longer than maybe a 20-minute presentation. And that's because it's really hard, especially as we're scientists and engineers, and we want everybody to be excited about the thing that we're talking about as we are. So the 3 minutes is really, really, really challenging. So with that being said, they've put a lot of time into it. And so I'm glad to see that we have the amount of people we have here. This is exciting for me. Hopefully you're here not only to support somebody, but also learn just more about what people are doing in our grad programs. So the rules, wait, I'm excited. What was I supposed to do? You're excited to be here? Anyways, we have, it's got to be your bowl. I don't know if you know that reference, but anyways, we have 9 presentations. They're 3 minutes each. If it's 1 second over 3 minutes, you will get gonged, and you will get gonged, and you will stop regardless of where you're at. So this is a challenge, right? And you'll be politely escorted, like Jessica's going to take you off the stage. We do have a slide that presents each person. I'm kidding. Yeah. I mean, kind of, it's up to her. I'm not going to usher you off, but.
And we will hold all questions to the end. So there are sheets out you can use for coloring, for paying attention, keeping track of talks, asking questions, and we'll do any questions at the end so that we allow the speakers to kind of keep their rhythm going without throwing everybody off.
Yes. Everybody's got 1 slide, 3 minutes. And we're going to have all the questions at the end. I'll introduce the speaker in that transition period to allow the next speaker to come up for those of you getting ready. Anything else? Oh, do you want to explain this a little bit?
Coloring sheet. If this is helpful to you to help pay attention or entertaining, there's crayons over there. And it's a little bit of a matching game. So see if you can figure that out.
Okay, it is a matching game. So with that, I will invite Mark up. So Mark Skinner.
Thank you. When does it start?
You tell us. When do you want it to start?
I guess I'll start. Are you waiting to hit something? Okay, I'll start right now. Okay. All right. Hello, everyone. I know most of you. I think I know everybody probably, but I'm Mark Skinner. I'm a 4th-year material science and engineering PhD student in Dr. McDougall's Food and Dairy Innovation Center. I received my Bachelor of Science also from BSU's chemistry department. Okay, so today I want to talk about a different type of chip. Is my poster up there? It is, yeah. Okay, so the sweet potato kettle chip. So, and the advantage that you have with pulse electric fields use with processing this food material, making it healthier. Okay, so PEF works because it applies an electrical field that places a potential across the cell's membrane, usually measured in kilovolts per centimeter. This field is delivered in a square waveform with a pulse width usually lasting about 6 microseconds. The total specific energy of the system is summed up usually measured in kilojoules per kilogram. Here, each pulse interacts with the ionic compounds in the cell to form pores. In the cartoon diagram on the left, you can see the relation and its effect on the membrane formed by closely packed phospholipid monomers.
Thank you, guys. Have a great rest of your day. You
The
too.
effects of PEF applied electroporation at the bottom left SEM image. Here you can see how the starch grains are retained despite position 65 can be mitigated using PEF. So even though the starch grains are retained, the electroporated cells are an ideal size to allow precursory acrylamide forming components such as free amino acids and reducing sugars to diffuse out. These precursory compounds are components in the Maillard reaction that, along with water, are essential for acrylamide formation. Okay, another advantage PEF provides occurs when the crust of the PEF of the treated material is smooth. As seen in the upper SEM image, this condition helps to mitigate the oil uptake during frying of the finished kettle chip product. So experimental tests I ran last year using liquid chromatography, triple, quadruple mass spectrometry, and Randall continuous extraction, they showed statistically significant results. The reduction of acrylamide and the production and the retention of fryer oil was statistically significant. In summary, PEF treatment is a chemical-free method that, when performed prior to frying, can mitigate acrylamide production and reduce oil retention with Covington sweet potato chips, thus providing a healthier product and reducing oil consumption. Thank you.
That was great. Great to start us. I know you disappointed Linda because she really wanted to gong you. But you did a good job. Kept it under 3. Yep.
Linda, if you ever just want to use the gong just to identify that it has gone to the next stage, you can, okay?
Thanks, Linda. And now, take it away.
Hello everyone, I'm Asfandiar Khan, a second year PhD student. And thank you everyone for your presence today. So I'm going to talk about my topic, which is about material design in a sustainable way with a focus on energy security. So starting from this figure on the left, so rare earth elements such as dipnosium and dysprosium, they are very critical in modern technology. They are used to make permanent magnets, which have applications ranging from electric vehicles to electronics, robotics, and wind turbine, even in the aerospace industry. And but the problem with, in fact, 90% of the electric vehicle motors today, they use these rare earth magnets to power them. But the issue with the rare earth magnet is that their global supply chain is very, very concentrated. In fact, today, 70% of the world global supply, mine supply, and 85% of the refined supply is produced from China. So with this concentrated supply chain, any disruption in the global supply or any geopolitical conflict can lead to, can seriously threaten the electric vehicle and renewable energy sector. So what we need are alternatives. And one good alternative compared to these rare earth magnets are called alnico magnets. Now, these alnico magnets have very good properties, but to make them as good as the rare earth magnets, we need a right set of material properties and composition to make them as good as the rare earth magnets. And finding this right set of material properties and composition, doing it experimentally, is not only time-consuming, costly, but it's very, very challenging because of the vast number of parameters we have to find. So this is where our research comes. What we do is that we use artificial neural networks to solve this problem. So think of artificial neural network as a biological neuron which takes an input and predicts an output. What we do is that we use the microstructure of these rare earth magnets, feed them inside a neural network, and it predicts us these critical parameters. Now, with these critical parameters and the composition, if used, we can make these alnico magnets as good as the rare earth magnets are. Now, with our research, we are solving 2 major problems. First, we are solving the serious problem of our dependency on rare earth magnets, specifically considering its concentrated global supply chain. And secondly, we are using innovative ways, sustainable ways to design new materials for future green technology. Thank you.
Thank you. Good, man, you guys are way better than faculty, myself included. We're 2 for 2, where we were 2 for 2 in the other direction during the faculty presentation. So this is exciting. You guys are way more prepared. Good job. Okay, Lila, it's all yours.
Hello, I'm Lila Towers, and I'm in Janae Siren's group here at Boise State University. I study PFAS, which is perfluoroalkylated substances, and it's a human-made molecule that was created for coatings about 100 years ago. They're pretty much resistant to everything. They're even used in photochemical resistant layers on top of wafers for semiconductor manufacturing, but they're also made for simple things like oil-resistant coatings in nonstick pans or popcorn bags, and waterproof coatings for your jacket or mascara. Sometimes these coatings are rubbed away, but the molecule itself is super strong and does not break down in nature. This is very concerning because when it flows into our streams, it goes into our oceans, which have huge waves that crash, create foams, and then spray this molecule into our clouds. So they can go anywhere in the world. They even will precipitate and rain down into our drinking water. It has been found in human blood, and it's been linked to several cancers and diseases. So many scientists are looking at ways to remove this from our body and from our environment and break them down. But it's very difficult because they're surface active, so many of our classical chemistry techniques will not be able to look at them at their most active form. Instead, I'll be using a surface active technique called some frequency generation spectroscopy. Basically, I'm taking a really cool ultrafast laser system and seeing how the molecule moves, wiggles, and jiggles so I can understand its structure, orientation, packing, or its impact on molecules surrounding it, and see not only the surface-specific impact that it has when it's at the air-water interface, but also understand the fundamentals of how it can be used to be removed from the environment, how we can use it for mimicking its resistant materials and apply it to different less toxic chemicals, or how we can remove it from our bodies as well. Interfaces are very important, so we can use the same technique to look at interfaces that are biological membranes or different areas. So not just PFAS alone. But hey, I'm just scratching the surface. Thank you very much.
Thank you, Lila. Good work. All right, now we have Nick. So when you're, all right.
All right, I think that'll work. All right, hi, I'm Nick Wright, and I'm going to be talking to you today about the materials used for quantum computing and how we can improve them. So quantum computing is poised to revolutionize the way we perform computations, which will unlock exact solutions to problems that are impossible to solve using classical computers. Quantum computing has been studied theoretically since the early 1990s, which kicked off a race to engineer materials that can host quantum superpositions. In 1999, Yasunori Nakamura and his colleagues presented the world with a device based on the superconducting Josephson junction, two superconductors separated by a thin insulating layer. Their device is capable of hosting quantum superpositions at the gigahertz scale frequencies. Since 1999, their device has been used to build functional quantum computers. However, these superconducting-based quantum computers have a major downside. It's not working. Here. Okay. Since 1999, their device has been used to build functional quantum computers. However, these superconducting-based computers have a major downside, which limits their scalability and vastly increases their cost. And that is that they're required to operate at millikelvin temperatures, which for context is orders of magnitude colder than the vacuum of space. So overcoming this low temperature limit has been a main focus in the field of quantum computing. And we here at Boise State believe we've identified a material that is capable of hosting such superpositions. Rather than utilizing electricity-based superconductors, we seek to use light-absorbing molecules as the basis unit for a material that can host a quantum superposition. When two or more of these molecules are in close proximity to one another, they share an excitation energy. When two molecules pack in such a way that their transition dipoles have a non-zero angle, there are two allowed electronic transitions. This is obvious in the steady state absorption spectra, which you can see in orange, which shows that when packed into a dimer, there's two optical transitions at lower and higher energy than the optical monomer. Theoretical work has shown that if these transitions can be simultaneously excited, there exists a quantum superposition at the terahertz scale frequency, much higher than the gigahertz frequencies of the superconducting quantum computer. However, detecting these superpositions in a lab is very difficult. They exist on the femtosecond timescale, which is a millionth of a billionth of a second. In order to overcome this, we've leveraged the expertise of Dr. Daniel Turner, and built a custom light source that's capable of generating 5 femtosecond pulses. Using these pulses of light, we believe we'll be able to simultaneously excite these transitions, and using a technique called femtosecond coherence spectroscopy, we will hope to be able to detect quantum superpositions in molecular aggregates, which could then be used for more reasonable temperature quantum computing. We're striving to do what Nakamura and his colleagues did in 1999 for a new material that overcomes this low temperature limit. And hopefully 25 years from now, you will see quantum computers based on molecular aggregates.
Nice job, Nick.
Nick, you made Linda so happy. I don't know if you saw her face.
Did. Yeah,
Yeah.
Jilla?
That was definitely more
Thank
Okay.
All right.
And yeah, exactly.
Hi, everybody. My name is Tiller Rector. I am a second-year PhD student in Dr. David Strada's group in the ANML. And the material that I've been working with is laser-induced graphene. It's very similar to graphene, which we know is a monoatomic layer of carbon atoms bonded together hexagonally in that honeycomb shape. Because of that morphology, we have a lot of really interesting properties. You have good electrical and thermal conductivity, really strong in-plane strength. Laser-induced graphene is similar to that, but it's mostly bulk graphitic regions with a lot of voids. And then around those voids, you have monolayer and multi-layer graphene. The way that you synthesize this material is implied in the name laser-induced graphene. You just shine a laser on an appropriate carbon-containing substrate, and really that's about the stipulation. Most carbon-containing substrates. So in literature, this has been done on bread, paper, cardboard, silk, coconuts, Captain, which is a polymer sheet, flexible sheet. And that flexible substrate, that choice of substrate is what's really interesting. So my research question has been, can I integrate this material into some sort of flexible hybrid electronic? And the answer is yes. But because this isn't pristine monolayer graphene, it doesn't have the conductivity that graphene would, or bulk metal. So if I want to use this for a circuit application, then I need to metallize it somehow. And copper is the primary choice. It's really cheap, inexpensive. It gets used traditionally. So can I put copper into my laser-induced graphene to make a flexible circuit? The answer is yes. And I accomplished that by putting palladium into my laser-induced graphene. Palladium is an extremely active catalyst. So if you put it in solution, it will selectively reduce copper ions, and you can plate copper on top of the laser-induced graphene, and you can make a flexible circuit doing this. That's interesting in and of itself, but what's the greater justification for this? Well, if you wanted to make a flexible circuit, one of the primary methods of doing that would be with photolithography, which is a lot of steps, but it's patterning with light. You have mask, you have exposure, you have development outside of that. And it's great. You get really fine resolution with photo, but there's a few drawbacks to that process. One, the chemicals are hazardous to people and the environment. Two, it adds a lot of process complexity. There's a lot of additional steps. And three, the cost of the equipment is tremendous, really, really expensive. So by comparison, the work, 90% of the work that I've done with this process has been with a 450 nanometer, 7-watt visible laser that costs $70 from Amazon. So theoretically, you could buy a laser like this and make this material in your garage. You could plate it in your garage. You can buy the chemicals for an electrolysis bath. But all of this is to say that I get to cut out a lot of complexity, have a direct right step with the laser, and I can still make designs, one-off designs, circuits, however, and make a flexible circuit. And I've done that. I've proved feasibility with that process. So thanks for listening.
Go take a breath.
Thanks, Attila. I think you might have had more words than most, but it was great.
Breathing is important. It's okay if you get hit with the gong, I promise.
That was awesome. That's right. And this is Scott Riley. He's got a questionable advisor, so we'll see how it goes.
Hello, everyone. My name is Scott Riley. My research is focused on the design and characterization of in-pile instrumentation and sensors for the measurement of phenomena such as temperature from directly within the core of nuclear reactors. Now, when we think about temperature measurement, specifically in currently existing reactors like pressurized water and light water reactors, which I have a schematic here on the bottom left corner, we actually don't measure directly the core temperature in these reactors. Instead, what we actually do is we measure the temperature of the water coming out of the reactor and the temperature of the water coming into the reactor core and back out the temperature. Now, what we wanted to do in collaboration with Idaho National Laboratory is develop a temperature sensor for directly measuring the core temperature. Not just that would provide reliable and accurate real-time data to reactor technicians, not just in general operation, but also during accident scenarios where we can start seeing fuel temperatures in excess of 1300 degrees Celsius. That way we can provide reactor technicians with as much information as possible in regards to the goings on within the reactor so they can make informed decisions. Now, currently, the most commonly used temperature sensor in the nuclear industry are thermocouples. And the reason that we don't just throw a bunch of thermocouples into the core and directly measure it currently is because there currently exists a gap in temperature sensing technology utilizing thermocouples when it applied to nuclear reactors. That gap is imposed by two conditions. One, when we think about irradiation-resistant thermocouples, like type K and N, which are nickel-based, these thermocouples, when they're exposed to temperatures in excess of 1260 degrees Celsius, they start to decalibrate rapidly, largely because of chemical instability within their thermal elements, meaning that during accident scenarios, these thermocouples do not provide a reliable temperature measurement for the reactor technicians. When we think about high temperature sensing thermocouples, which are platinum-based type B, C, and S, which operate between 1500 and 2200 degrees Celsius, these thermocouples undergo rapid decalibration when exposed to the thermal neutron flux present within the core of the reactor, largely due to the rhenium-rhodium alloying content. So what we wanted to do is design a thermocouple and characterize its stability that combines the high temperature sensing capabilities of the platinum-based type B, C, and S with the irradiation tolerance of a type K and N. In doing so, we were able to produce with the Idaho National Lab a thermocouple called a Hydro-TC, which is composed of niobium and molybdenum thermoelements and is actually commercialized at the moment. It also received an R&D 100 award in the year 2019, partially because it holds the record for the highest sustained temperature measured with no measurable drift within a reactor core, which was in the advanced test reactor over at the Idaho National Lab. That was actually dead on.
Thank you, Scott.
Thanks, Scott. He's my student, so of course he went over. That's how we train. Just kidding. All right, now we got Maya.
You are allowed to time yourself. Although if you don't breathe like a tail, I'm gonna be worried that someone's gonna hit the ground.
I will breathe. I like to see the time. I'll just put it right here. Okay. Right, yes. Hi, I'm Maya Ketterich. My work focuses on a type of molecule called a dye. A dye is kind of an umbrella term, but for our purposes, a dye is a type of molecule. We care about the ones made of carbon, the organic dyes, that when you shine light on it, it will absorb that light, absorb that energy, and go to an energized or excited state. When it discharges that energy, it releases some light again. One key interesting property of these dyes is that when you bring them close together and in the right orientation, they can share that energized or excited state across multiple dyes. And this changes the properties of that excited or energized state. You start seeing some new and interesting properties. This particular phenomenon has a lot of applications in things like solar cells, in things like understanding of photosynthesis, and in particular for the QDNA group, which Nick is also presented as part of, for quantum computing. You can use this special shared excited state as a fundamental unit for quantum computing, theoretically. In order to realize this special excited state, you have to be able to bring the dyes close together and control their orientations. What we do in the QDNA group is we use DNA to try to do this. We use it to bring the dyes together and to control their orientations. We attach the dyes to the DNA, and we can use various different types of sort of 3D DNA structures to do this. It's a picture up here of one particular one with 2 dyes on it. We use DNA because it's particularly stable, it's easy to predict the 3D structure of, and it's easy to attach dyes to. What I do for my work, I do modeling and computation. So I do try to optimize the properties of the individual dyes to maximize that shared excited state phenomenon. And also I do on the larger scale modeling of those DNA dye complexes to predict the orientations and identify good DNA structures. On the small scale, we use quantum mechanical sort of first principles methods to predict these dye properties, such as dipoles, et cetera, and also use machine learning methods. On the large scale, we use more classical methods like molecular dynamics to look at these really big systems and test out different DNA structures. We also directly compare with experiment. We both validate our models with experiment and help guide our experimental collaborators.
Great job, Maya. Kincaid. Awesome.
Hello, everybody. I'm Kincaid Graff. I am a 4th-year PhD student in Dr. Claire Zhang's Electrochemical Energy Materials Labs. Specifically for my, what's it called? What's this thing called again? 3 minute what? Well, okay, for my talk, I work on the optimization of sodium ion layered metal transition metal oxide positive electrodes. In all of our mobile devices, we have a battery within it. And how these batteries work is as a rocking chair. There are cations that flow from one electrode to the other and back. And this instigates an electrical current that our devices use. However, a lot of contemporary batteries utilize very unsustainable materials, your lithium, your nickel, and your cobalt. These are all very expensive. These are all not very abundant, and they're very susceptible to price turbulation. So with sodium-ion batteries, we're trying to negate these effects with more sustainable materials, your iron and your manganese. These are very abundant, cheap, and very stable against any sort of price turbulence. So with these two fundamental concepts in mind, both the operating principles of a battery and the sustainable ethos driving this gives creation to what I like to call the 3-tier optimization. First, we try to start off with a fairly sustainable composition. Let's look at this one. It has a little bit of nickel in it. I know I talk trash about nickel, but it offers a lot of energy. It can be fairly good in small quantities. Has a lot of manganese. I love manganese. And what we can do is by altering that sodium content, we can actually instigate new structures that form. We want to optimize this structure. And by differing the sodium content, we can create multiple structures, a P2, a P3, and a mixture of the both. And what happens now is we hook these up to our phones and we cycle them. We want our batteries to last, let's say, 1,000 cycles. So if your phone is dying after 50 days of usage, it's not a very useful battery. And this correlates to the stability of those lines on that bottom left graph, your bottom right. The red one is the most stable. And what that means, it'll last for much longer. So from this, I can deduce that the most optimized structure within my material is the P2P3. However, is my composition optimized? I don't like nickel. Let's replace it with some iron. However, when I replace that nickel with iron, that's of course is going to modify my structure. It's going to modify my properties. So what I have to do is I have to optimize with all of those in mind. I have to make a very sustainable composition. I have to have a very stable structure. And I also have to have a very competitive electrochemical performance if sodium-ion batteries are to be competitive for future usage in relation to contemporary lithium-ion batteries. Thank you.
Thesis, that was the word.
Good job.
Great job. All right, our final lightning talk speaker is John Martin.
Yes, indeed. Hi, everyone. Whoa, that was very loud. I want you to imagine that every sort of adult who's buying baby formula for their kids relies on a single factory, okay? And one night that factory shuts down. And so over the next couple days, parents are going to the store trying to buy baby formula to feed their children, and the shelves are looking more and more empty. So there starts to be a panic. People start to, hoard and buy it. And there's anxiety and there's rationing of the baby formula. Okay. That actually happened. Did anyone here experience that? It happened in about 2022. There was like a bacterial infection at a baby formula plant. There's only one. Well, there's actually a couple, but there was just a couple, right? So even just one major crisis caused a massive shortage. Okay. Now I want you to imagine that there's an analogous situation. Okay. So instead of baby formula, there's critical materials. And instead of it being one factory in Michigan, it's one country, China. Okay. Making sense? And imagine further that China decides to invade Taiwan. That could absolutely happen. What would it mean for these critical materials that are essential for our energy infrastructure and for our national defense? I mean, if China's invading Taiwan, we probably want to be able to produce more planes, right? But if you don't have the magnets, you can't do it. So that's a problem. And we're trying to address that problem. But it's more than just a vulnerability there, right? It's not just that there's a single lifeline. It's also that these materials are really expensive. Like Han said, neodymium and dysprosium are really pricey. In fact, if you want to build a giant offshore wind turbine, you need to spend about $1 million just for the wind turbine. Not considering all the concrete and the steel that's in there, just for the magnets, okay? So we need something cheaper, and we need to have more than one lifeline here. And that's why we think manganese is a good option. Now, it's very challenging to make manganese into a magnet because it's not naturally ferromagnetic. But we find that if you put it with some aluminum, you can get a nice ferromagnetic phase. Now, another challenge is that that's not thermodynamically stable. Put a little bit of heat on it, it likes to fall apart. We think we've solved that with gallium. Put a little bit of gallium in there. Another problem is that it's not magnetically hard. What that means is that it doesn't like to stay a magnet. It's very easy to demagnetize it. We're trying to solve that problem right now by putting boron in there. It's pretty hard to do. We're also trying to fold the metal up with a technique called severe plastic deformation. Put a bunch of dislocations in. We think that'll help the magnetic hardness as well. I think this is a great idea. Think about it. We have more than one lifeline. There's not one factory that produces baby formula. There's a bunch. Brazil, Australia, the US, Idaho has manganese. That'd be cool, right? And I think it's values that we all share. Sustainability, innovation, self-reliance, more security. We should do this.
Great job, John. I think, can we do just a round of applause again for our speakers? So I really want to say thank you guys for following the format. It's not easy, as I didn't make the time last spring. So you guys did a really, really good job. Do you have anything before we start questions?
For questions, I was thinking we could have all of our speakers come up together and stand together. So that way you're not standing by yourself answering questions. And so we have questions. And once we have you all here, we want another round of applause for you here. And Sarah will probably also take a picture. But who has questions in the audience?
Okay. Here, you get.
All right. Archer, who's your question for?
Thank you, first off.
Hello. I just was curious, what do you hate so much about nickel?
So
Go.
I'm going to try to not get political here, but I believe it's about 60% of grade 1 nickel that we use for batteries originate from Russia. Not a huge fan. Along with that, a lot of nickel in Indonesia. Though I don't have anything against Indonesia. Don't like Russia. I'm sorry if anyone's from Russia. I mean, obviously, a geopolitical opponent containing 60% of a material that we really need for future proliferation of renewable energy and electric vehicle makes it a not very reliable material. It's also very toxic. And for sodium ion batteries specifically, lithium is proliferating toward a very nickel rich material. They want to have LiNiO2. We can't use that for sodium ion materials then. We have to offer a sustainable alternative, not just the exact same thing, but worse. So thank you for your question.
Thank you. Other questions? Oh, Sarah.
Who's your question for, Sarah?
So you cryptically said something about how it's difficult to put boron in the magnets. I was wondering if you could elaborate on that a bit.
Yeah, well, we actually, maybe that's not totally accurate. We're finding it very hard to figure out where the boron goes. Boron's so light that it's hard to like characterize where it's at. So we might have it in there. We just don't know.
Thank you.
Another question? Scott, I have a question that I forgot to ask at your defense. No. I'm kidding. I don't have a question. Other people, questions? You have 9 presentations. There's got to be questions. Okay, I have a question. Mark.
Yes.
For you
Yes.
do pulsed DC surface modifications. So we use, in my lab, we use pulse DC. I'm assuming a lot higher potential, but I don't know about durations. Maybe if Nico probably knows.
We run ours at essentially we go like a 24 centimeter gap that's about 24,000 volts per. Yeah, so it equals out to be about 1 kilovolt per centimeter.
Gotcha. Does it cause, so I think you said that it caused it smoothed the surface, but it also caused something not to form, if I remember right.
Not to form.
Not to form like the cancer causing.
Oh, acrylamide. Yes, yeah.
Yeah.
So yeah, the carcinogen. I would have elaborated more on that, but I was like concerned with time. But yeah. So yeah, right. So you have the precursors of a amino acid, free amino acids, specifically like asparagine and glucose and fructose, the reducing sugars. If you don't have those in there, those are like really big in the Maillard reaction for forming acrylamide, the suspected carcinogen or proposition 65 and stuff like that. What about it though?
Well, I guess I was going to ask, like, does it, so we use it to like cause heating. So you have problems with heating using this process.
So that was actually one thing. They do call it they say non-thermal, but that also might be the sales team saying it's non-thermal. The rise in temperature, it happens, but it's not significant in the way they have it set up. Now, of course, our conducting material is often just tap water or salt water. We increase the salinity of it, of course, to get a better conductivity. But it doesn't really heat up very much. Like it doesn't heat the stuff up very much for us.
Lastly, is this a continuous process? Like you just have like a tray and it goes through and.
So the way we used it, there's multiple systems. We have a batch, we have a fluid, and then we also have, like you said, a continuous. So there is a conveyor belt. So we actually have the I believe like the B2 continuous system. We go through this company, a layout of Germany, and they can continuously, like you can throw green beans or sweet potatoes or whatever, sugar beets through there, and it'll continuously do it. You could run it on an industrial scale very easily. Yes.
Cool.
Yeah.
Other questions? Jake,
who's your question for? All right, you can take this one.
Hey, Maya.
Hello.
So I kind of have like a 2-part question, I guess, for your topic. So you say like the dyes are like attached on this like DNA scaffolding thing. Is it an actual nucleic acid, or could it just be like any double helix that spirals and repeats itself? Or does it have to be like a nucleic acid, or is it even a nucleic acid?
We do use nucleic acids, DNA. You could attach it to a lot of different things. In nature uses protein. I think so. Nature uses proteins, like in photosynthesis. This is very similar in a way to photosynthesis. So you could use different large macromolecules like proteins. But proteins are a pain to get to do what you want them to do. And DNA is super easy to predict the 3D structure of. There's a whole field of DNA nanotech where you can make wacky things out of DNA. So we're kind of using that to put put dyes on and scaffold it. You could use other nucleic acids like RNA as well, but RNA falls apart if you look at it weird. So
Okay, thank you. And then these like scaffolds, where are they comprised? Like, are they in the supercomputer or quantum computer like wiring? Or like where exactly are they stored?
we don't have something like a circuit built yet. We're still working on kind of getting it working towards that, building the actual system, but it would be sort of like the logic circuits.
Okay.
Yeah.
Got it. Thank you.
Yeah, thank you.
Peter, here's your question for.
I shouted out.
No, because Zoom won't be able to hear you, but who's it for?
They just want to get the mics.
Oh, sorry. My question is for Lila. So first of all, congratulations to all of you. You did a phenomenal job in conveying a message and making this in 3 minutes. It was just cool to see you all here and hear you all. I really liked, Lila, your presentation because of the picture. Well, not only because of that, but your picture of the waves really conveyed the message of here is this super stable molecule that is out there, and the wave sprayed it into the clouds, and now it's all over the planet because of that. Now, I think you understood somehow that you have a strategy or you research a strategy how to break down this molecule and how to, but what I don't know, understand what the strategy is to actually get all these molecules that are out there back, or what is the strategy to actually remediate this problem that is now so diluted all over the planet?
Yeah, that's a really great question that our lab doesn't work on. Sorry, we do fundamental research to understand how these molecules are impacting the world around it. I'm looking at how is it reacting at different temperatures and different pHs, so I know what it looks like when it's on the surface of these nano aerosols and clouds, but I'm not actually looking at how I can remove it. I'm hoping that my research can inform someone who does this removal process. Right now, there's not a lot of scalable degradation mechanisms, but there are many, many research groups looking at how to break these down and are very successful at it. But removal, totally different question as well.
Thank you. Other questions?
All right, Kincaid has a question.
First.
Wait,
I have a
can
question
wait till
too,
after.
and it's actually for Kincaid, so that works out. I was wondering, what are some of the characterization techniques that you use for quantifying your structures that you're trying to fine tune?
Great question. So I do a lot of X-ray diffraction in Dr. Ubik's lab. So typically, if you're just looking for the crystal structure, one thing you can do is, of course, XRD. Another thing that is very important to batteries is kind of how the sodium ions influence the structure while they're being taken out and putting back in. That requires the use of Rietveld refinement, a computational technique that can look at an XRD scan and actually fit a structure to it down to pretty much how far apart those atoms are. Furthermore, if we have like a P2, P3 intergrowth, let's just say two structures, you can use TEM also in Dr. Ubik's lab in order to actually see where those phases grow within the same particle. So typically XRD, which requires computational analysis, and then TEM. So great, thank you. I may as well just ask my question now. So question for Attila is, from my understanding, I'm not a semiconductor guy. I apologize. I fall asleep at the mere mention of the word. Sorry to the semiconductor people. But so from my understanding, you're taking this $70 laser off of Amazon, and you have a sort, a liquid or a gel on maybe silicon that you fire with the laser, and it causes it to solidify. Am I correct? I mean,
Steal the microphone from
steal
Kincaid.
very quickly.
We don't want Kincaid to have the microphone for too long.
Not quite, and it's interesting, but what the process actually looks like is taking this polymer film capped in by a trade name polyimide, just like a sheet inflex. And at the most basic level, you just take that film and you just expose the laser to it, and you deliver fluence through the laser, and you get this violent photothermal conversion from whatever the chemical structure of polyamide is to just mostly carbons bonded together in that hexagonal structure. But when we're talking about including nanoparticles, palladium, something like that, the approach, you can do both bottom up and top down methods. But my approach has been take palladium nanoparticles, stick them in a solution, spin cast that solution on top of the film, let it dry, and then laze over it. And during the conversion of the substrate into LIG, it kind of bubbles up and incorporates the palladium. You could also make LIG and then submerge it in a bath to sensitize it. That would be a good route to incorporate nanoparticles. So.
All right. Other questions? There was one. Oh, Noah, that wasn't the one I was thinking, but that'll perfectly.
Noah, who's your question for? Scott.
So it's to my understanding that thermocouples are the electrical potential difference between two dissimilar metals. Have there been any issues with galvanic corrosion in the Hyder TCs? And are there like any methods to mediate the galvanic corrosion in TCs?
So in case of, I think this is on. So in case of the RTCs, not so much, to be honest. Actually, the biggest problem that was posed for the Hyder TCs was not corrosion in that sense. It's the CT mismatch. So one of the key things in this system was actually in that hot junction was how to actually construct it in a way that you get a reliable system mechanically with cyclic cycling with temperature. Because these were first proposed back in the 1960s, but it took all the way up till the 1990s and early 2000s to actually realize how to form that hot junction. That was facilitated through swage and tantalum ring about the niobium molybdenum thermal elements, which takes into account that CT mismatch with cyclic fatigue through thermal cycling.
Other questions?
I had a question for Khan. About these, you mentioned that you're using these neural nets to, refine the parameters for the Alnico magnets. What sort of parameters are you looking at?
So we like for this specific case, we are like interested more in the like forcible coercivity of the magnets and the composition of each element inside the material. And what we do is like we give them the microstructure as an input to the network. And then the network adjusts the inside of it, which has weight and biases in the structure. And then it spits out these parameters. And in the combination of these, and in our specific neural network, we use, it's called as a physics-informed neural network. So unless the physics is not satisfied, the solution will not be correct. So the parameters it will predict will satisfy the physics. And these parameters then can be used to make a whole new material, which will have the exact same properties as the rare earth magnets. But like we'll be using different materials.
Thank you. Lauren's got a question.
Lawrence, who's your question for? Nick. Everyone's gotten a question now.
Hello. So mine's maybe a little too physicsy for the purpose of a question in this type of setting. But I found one of your papers because I'm really interested in the work you're doing. And in here you say decoherence is the decay of a superposition with time. What does that mean? A decay of a superposition?
Yeah, so the superposition effectively exists as when you detect it, you see the oscillation of a signal between two things. So in the Josephson junction that I was mentioning earlier, it's effectively the existence of an electron on the left or the right side of the junction. And so if there were no environmental fluctuations surrounding that, that would go on forever. However, the environmental fluctuations that surround it will interfere with the hopping back and forth effectively, and cause that superposition to fall out of alignment. And so this is a process that happens really, really quickly when there's a lot of environmental fluctuations, which is why, as I mentioned, they operate these things at millikelvin temperatures, because when you cool down that low, you limit the environmental fluctuations. And so effectively decoherence is the process of the superposition being unable to continue its hopping back and forth, if you will.
Great. Richard, Mike, Paul, Ryan. You guys have good questions all the time. But not today.
Is it time for a
Where's the
final
shot?
gong? Oh, Dr. Molnar's got one.
Yes.
I think Mike is itching with a question too.
Attila. Well, Attila, you mentioned that we said you can do this in your garage for $70. And well, I asked you that question back. If you can do this for $70 in your garage, and this has these cool properties and provides new technology, new applications, have you been thinking of, or do you know somebody in your group that is thinking of actually commercializing this and doing a startup or something like this? What would it take to get there?
Yeah, that's an interesting question. So there's a lot of process variability with forming LIG. So where photolithography, you get extremely sharp, well-defined edges. With LIG, you tend to have very messy, incongruent edges just because it's that violent photothermal expansion. I think LIG could fit into this spot where you have like tens of micron scaled things. I'm not really sure what's preventing commercialization besides proof of concept and having it reliably function. So there's a lot of ways I could go with that answer. There's some investigation into bend testing structures for reliability that we've done to 10,000 cycles. That works. It's probably impact and shock resistant. That remains to be seen. But as far as an analog for something being done out in the real world, it's a similar process. It's not laser-induced graphene, but American Semiconductor, a company that produces flexible circuits, they use a similar method with a laser to ablate a copper film to create the traces. So they're not forming laser-induced graphene, but they're forming their copper patterns by ablating the negative of the copper pattern with a laser. So there's probably room, and I guess I don't know how to answer that more fully at this point, but thanks.
Great question. Like the full circle. Yeah, it's great. Other questions, or should we? Oh, Brian, yes.
This is for Lila. So you mentioned your some frequency spectroscopy tells you certain structural parameters like orientation. What do you find is the most important for your current research? What structural parameter that you can measure?
That is a wonderful question. For my research right now, I'm very interested. The compound, of course, has been well categorized because it's of such great interest, but like the orientation is well known. I'm more interested in how the structure is changing at different temperatures. One thing I didn't mention, my research is more related to ice nucleation and ice creation, since it's very effective. PFOS, PFOA, super effective at making ice. It's in our clouds. It could change our climate. Oh no. And it turns out that there is a change when the bulk pH is held constant. Temperature induces a pH change of the surface molecules. So right now, temperature.
Great question and great answer.
Thank you.
Okay, I think we're gonna
Going
wrap it up.
once,
I know
twice.
Brenda wants, what, there's another one?
No, going once, going twice.
Oh, on chat, great.
Does messing with the oil?
For who?
Nick would like to know if messing with the oil makes the potato chips taste different.
Well, there's a couple things with messing with the oil. Hopefully tidying up the oil is a better way to put that. But yeah, so using less oil. So obviously, if you want the most bang for caloric content, oil is the highest one. So the higher oil content you have, super saturated, you are you gonna gong me or okay? Anyways, but the super, yeah. So the super higher, it's a health concern with that, like, you know, with obesity and all that stuff. But then also too, there's two other ones too. So shelf stability. So like having a highly oiled chip on the shelf, it's not going to last as long. It's going to degrade the product, oil oxidation and stuff like that. But then I'm trying to think of the other one. So we had, yeah. So the health concerns that, and then also too with industry, the more oil you can leave in the fryer where it's supposed to be, the better it's going to be, more economical. So save money, save product that way too. So does that answer Nick's question? Okay, cool. Thanks.
I don't think Harold has a real question. He's just concerned about Attila and Peter playing with lasers in the garage.
That's a lot of power. Asking that because he has his own 7 watt.
Yeah. Harold, you should not be playing with lasers in your garage.
All right, any other questions? Okay, I think this was awesome. Thank you guys, you did awesome. Let's congratulate. Woohoo!